Hi, let's talk about the process of finding empirical formulas. So let's begin by reminding that the empirical formula is the lowest ratio of the elements in a compound. So in this case, with lead and chlorine present, we need to figure out which formula of lead and chlorine are there. Now, since it's the lowest ratio of atoms, what that means is that we're going to use units of mole, because mole is how you count atoms, which means grams must be converted to moles. And so that's what we're going to do. We're going to take what's given here and convert each one to moles. So what you, like always, you write your given, 0.6, what was that, 884 grams of lead, and then using the molar mass of lead, which is the let's see, right here, 207.2 grams per mole times 207 oops, hold on a sec. And we're going to do something with the molar mass in order to convert it to moles. And the reason why that was bad, don't start with numbers, start with units. And first thing I'm going to do is I'm going to realize I need to put grams on the bottom so that grams of lead can cancel grams of lead. Now I need to figure out how to convert this to moles, so I'm going to put moles of lead on top. And then once gram cancels gram to give mole, I then use the mass, the molar mass of 207.2 grams per mole, and I put that here, 200 and, see, what was that again? 207.2 grams is the mass of 1 mole of lead. So that will give me the that will give me how many moles of the lead are present, which is this number right here. So that number we're going to use temporarily. And so let's see, 0.003322394 moles of lead. And then I'm going to do the same thing for the chlorine. 0.2356 grams of chlorine times, and then we're going to do the same thing, moles of chlorine over grams of chlorine, in order to ensure that it's clear that we're going to have gram cancel gram to give moles. And 1 mole of chlorine is 35.45 grams according to the periodic table. So why, now one might remind yourself, pure chlorine gas is Cl2. Shouldn't it be 70.90 instead of 35.45? And that's true for pure chlorine gas, but we're not using pure chlorine gas for this. This is chlorine as part of a compound, and when it's part of a compound, you assume single individual atoms, not Cl2s, no Cl2 molecules. So for that reason, I leave it like this, and then I'll do the math, giving that number of moles, 0.0066459 moles of chlorine. You'll notice I've made no attempt to round these because they're not the final answer. That's why I haven't bothered with scientific notation either. What I will do, though, is now I have the number of moles of each. Remember that number of moles is the number of atoms, or it tells you how many atoms, which is good. We're getting closer to our formula, which is the ratio of how many of these to how many, or how many to with relation to each other. The next thing I do is divide both sides by the smallest number. 0.003 is smaller than 0.006. So divided by 0.003322394. Yeah, it's a unitless quantity because we're just doing a ratio. Divide them by the same number, 0.033222394. So obviously, when you divide this by the same number, that's 1 mole of lead. And for the other one, it comes out to that, which is so close to 2 that we can just call it 2. And not paying attention, let's put the correct unit on there, or the correct element on there. So what it's really saying is for every 1 mole of lead, there's 2 moles of chlorine. So a 2-to-1 ratio, so there's 2 leads for every 1 chlorine. Oops, got that backwards again. Let's fix that. 1 lead for every 2 chlorines means that what you're looking at is a formula of PbCl2. That's how the ratio gets turned into the final answer. And we box that and then have all this as evidence of the work done in order to reach that. That's the empirical formula. Empirical formula. Yeah, get rid of that little extra right there. All right, now having mentioned that, if you look at this next question down here, the process will be honestly no different. It's going to require you to do the same thing using the same sorts of steps. Convert each of these to moles, divide by the smallest number of moles, and get the ratio, and the formula is going to be the same order with carbon first, hydrogen, and then nitrogen, and finally oxygen. But the process is the same as here. So I'm not going to bother solving that because it's just the same thing. That said, I suppose I certainly could show some of the steps and the final results. So this is what you get when you convert all the masses to moles. And then what I've done is divide, this is the smallest number, so I divided all of them by the smallest number to get a ratio that comes out approximately to these numbers. And then that tells me it is 1 carbon for every 3 hydrogen, for every 1 nitrogen, for every 2 oxygen, which gives me a formula of CH3NO2 as the empirical formula. So, having done that, onward to a couple of others. Let's see, let's just get the thing all adjusted like, okay. Now, let's consider how to handle these other ones. So suppose you heat aluminum in the presence of pure chlorine. It has an initial mass of that much, and then it increases to that much. Calculate the empirical formula. So here's what that means. An initial mass of this, that means you have 1.271 grams of aluminum. When the mass increases to this means the total mass of the aluminum and the chlorine that bound to it. So this is a combined mass. So what I'm going to do is be like, okay, so the combined mass of 6.280 grams is aluminum plus chlorine. If I subtract out the 1.271 grams I had of just aluminum, what that will do is tell me how much, and it's this much, of it must be just the chlorine. 5.009 grams of just the chlorine. Not Cl2, because when it's pure chlorine, yes, pure chlorine is Cl2, but when it becomes part of a compound, it's no longer Cl2, it's just Cl, because now instead of being by itself, it's bound to the aluminum. Sorry, that's supposed to be aluminum. Okay, so that's the mass of the chlorine. This is the number I'm going to do calculations with over here, 5.009 grams of chlorine, not Cl2, because it's not pure chlorine, it's chlorine that is a part of the compound. So let's do the math now. That means we're going to have to convert each of these to moles, and just like earlier, we're going to convert to moles and then compare the moles to each other. So that means I'm going to put grams of aluminum on the bottoms and then moles of aluminum on top. That way gram cancels gram to leave moles as the answer. And then same thing for the other one, so that I can have the answer of moles of chlorine. We then fill in the molar masses from the periodic table, which shows us that 1 mole of chlorine is 35.45 grams, so 1 mole is 35.45 grams, and with aluminum the number is 26.98 grams. So when we do the math on this, we're going to see what the number of moles is. So it's this divided by this equals that many moles of aluminum, and then of course doing the same thing here, we have this many moles of chlorine. So just as before, we're going to divide by the smallest number, which means divide by 0.04710.897. We'll divide both by the smallest number, 4710897. If it's unitless because we're just trying to find a ratio here, we're just dividing by the smallest number. So when that happens, this is what you get. Divide by the smallest number. This is the smallest number, so obviously it's just 1. and then turns out this is 3 times as big as this, so 3 moles of chlorine. So that is a 1 aluminum to 3 chlorine ratio. I don't know why I put those 2 dots there, but a 1 aluminum to 3 chlorine ratio is AlCl3. Now, could you have known that by looking at the periodic table and knowing that aluminum is a +3 and chlorine is a -1? Yes, you could have known that. This could have been predicted, but the point is, like, this is, how do you even know that that's true in real life? This is the math behind how we know that that is true and how you could confirm it in the laboratory. Now, you notice I've already set up this next one, 10.-9b, because this one's got an extra wrinkle, so to speak, an extra step beyond what you saw here, where you simply add your 1:3 ratio and you're done. Consider that it works the same way to begin with, so we have our initial mass of 38.33 grams of iron metal, and you heat it up and it increases in mass because it reacts with the sulfur. So it reacts with pure sulfur, which means this was originally the iron that you start with, and then this is the combined mass of iron and sulfur. So I take this combined mass that you end up with, subtract out this initial mass of just iron, and we take iron plus sulfur, subtract the iron, you get just the sulfur. That's the mass of the sulfur. So I take that mass of the sulfur right here and convert it to moles. That's what this is, number of moles right here. I took this mass of iron, put it right here, use the molar mass to convert to moles. So this is the moles of iron. And you'll notice the moles of iron, this number is smaller than this one. We need to find a mole ratio. So I divided both sides by this number. This moles of iron is the smallest one. So this divided by itself is going to have 1 mole of iron. This moles of sulfur divided by this, which came from up here, comes out to this. So okay, I've gone from my moles of iron and moles of sulfur divided by the smallest one, and now I have a ratio of 1 mole of iron for every 1.5 moles of sulfur. Oops, 1 iron for every 1.5 sulfurs. That's supposed to be an S, not 155. How do you handle that? Because you can't have a formula of Fe 1.5S. And the answer is you need to figure out a way to increase this ratio to make it to be whole numbers. What do I mean by that? You can't have you can't have decimals like this. So I'm going to try multiplying everything by 2 times 2. Will that turn it whole? 1 mole times 2 is 2 moles of iron. 1.5 times 2 equals 3 moles of sulfur. That does make it whole. That's great. If that didn't work, I would have tried timesing it by 3, and if that didn't work, I'd try multiplying it by 4. I would keep multiplying by higher and higher numbers until I get this turned into a whole number. But luckily, all I had to do was multiply by 2, and bam, they're both whole numbers now. This is better. Now it's saying we have a 2 iron to 3 sulfur ratio. And that we can turn into our chemical formula of Fe2S3. So that's how you deal with it when your ratio of moles does not give you a right straightaway whole number. Now let's look at some stuff on the back. So now on the back side of this page, notice that I've already completed the whole thing, but probably because of a mistake on the previous take, but also because it's nice to see the whole thing done. Let's talk about how you do the empirical form of a compound that gives you percents. We assume a 100 gram sample, and so that's why we're going to say 65.95% is 65.95 grams, something for 35.05% becoming 34.05 grams. Sorry, I said the wrong number, but you get the idea. This just becomes grams. So I take this number of grams of barium, put it here, take this number of grams of chlorine, put it here. And then I use the molar mass of barium, because grams cancel grams to give moles, because I want moles. So what happened here is I converted to moles of barium. And then likewise, converted to moles of chlorine. That's the moles of chlorine. As a note, notice that I didn't put Cl2, just Cl, even though it's chlorine. People sometimes are like, wait, isn't Cl2 mean 70.90 instead of this? The answer is no, it's not Cl2 because it's in a compound. Cl2, chlorine's only diatomic when it's by itself as a pure element. So it's not chlorine, Cl2, it's chlorine, just individual Cl. So anyway, at this point, you have your number of moles. What you do is you divide by the smallest one. See how that top one is smaller? That's why I divided by both sides by that smaller number of moles. And dividing this by itself obviously gives 1 mole barium. And dividing this by this one gives a number that comes out to approximately 2 moles chlorine. So it's a 1 mole to 2 mole ratio, which means 1 barium to 2 chlorine. And that's where the formula of BaCl2 comes up. All right, now as we look at 10-10b, let's look what we're doing here. So we have a percentage again, so we're just likewise, we're taking that 33.88% copper, assuming a 100 gram sample, and just replacing percent with grams, doing the same thing with nitrogen, and doing the same thing with oxygen, just replacing the percent with grams because we're assuming a 100 gram sample. Now what I've done here is set up a conversion to turn to moles, because in order to find the empirical formula is the lowest ratio of atoms, and since mole is the number of atoms, the ratio of moles will give us the empirical formula. So here we see grams, and we convert grams to moles by using the molar mass. Notice gram on bottom allows gram to cancel with gram. Mole on top allows mole to be in the answer. And since the mass is the, there we go. And since the mass is here for copper, that is the number of grams that a mole weighs. That's why we put the number here on bottom, because the 1 mole has a mass of that many grams, 1 mole is a mass of that many grams, or 1 mole of oxygen is a mass of that many grams. So that converts each of them to a number of moles. And we're going to divide by the smallest one. So that means, of course, this is the smallest one, so we divide all of them by that. And of course, if you divide this by itself, it's just going to be 1 mole of copper. And then if you do the math on this one, it comes out to about 2 moles of nitrogen. And then this one here, if you divide these, it comes out to roughly 6 moles of oxygen. So we're going to go in the order presented, which means the formula will be presented as 1 copper, 2 nitrogen, and 6 oxygens, like that. Now for the next one, I've already started the process. Same thing, when you have a percent sample, you just replace percent with grams, because we assume 100 gram sample, so that many grams of manganese, that many grams of oxygen. And then use the molar mass, so have gram cancel gram to give mole in the answer. And this came straight out the periodic table. It was merely rounded to the hundredths place, as we do with our molar masses. And what that does is it gives us that number of moles for each. Okay, once we have the mass moles, what we're going to do is determine the empirical formula by finding a ratio of the atoms. And since mole is merely a measure of atoms, we're going to, ratio of moles tells us the ratio of atoms. So the ratio of moles will give us what we need. Divide by the smallest number, it's clear this is the smallest, so when we divide both by that, it looks like that, and clearly this divided by itself will give 1 mole of manganese, and this one divided by that will give something a little interesting. It gives that. And what is that? Well, we're generally around these hundredths plates or so, so we're going to call it 3.50. 3.50 moles of oxygen. So what this is telling us is that we have a ratio of 1 manganese for every 3.5 oxygens. And that's not okay to have a formula of MnO3.5. We can, however, multiply these until we get a whole number. So I'm going to try multiplying both by 2 and see if that makes them whole. If not, then I'll times it by 3. If not, then I'll times it by 4. If not, then I'll times it by 5 and keep on going. So what happens if I multiply by 2? 1 times 2 is 2 moles of manganese. And I just realized earlier, my bad, that I made a mistake and put the wrong one. At any rate, so if I take this mole of manganese and multiply it by 2, then it's 2 moles of manganese. If I take this by 2, it equals 7 moles of oxygen, and that is a whole number. So multiplying by this by 2 gives a whole number, so I don't need to try 3 or 4 or 5 or 6. This just works. So what I've got is a 2 to 7 ratio. That's Mn2O7. we'll box that as the final answer.